For 30 years, I've watched this all unfold, and the most common mistake people make is thinking this is a problem of policy or funding or even political will. It's not of those things. This is a problem of physics. It's about irreversible decay. What we're witnessing isn't some new crisis we can manage. It's the final stage of a long, quiet collapse.
The thesis here is simple, and it's stark. The industrial and human foundation we need for any kind of strategic competition, well, it was systematically taken apart over 30 years. And look, this wasn't some hostile act. It was just a series of rational, short-term, market-driven decisions that, when you add them all up, have produced a strategic catastrophe.
And here's the heart of the matter. You cannot fix this with an executive order. You can't solve it by throwing a bunch of money at it in a new budget. Rebuilding heavy industry, recreating lost material science, regenerating decades of human expertise, these things operate on physical timelines that are completely immune to political pressure. The process that began back in the late 1970s is now picking up speed.
To really get what's happening now, you have to look back. Even in the 1970s, as nuclear plant designs got bigger and more complex, our own domestic giants, companies like Bethlehem Steel, they found themselves shut out. The specifications simply outgrew our industrial base. So this isn't some new gap that just appeared. It's a chasm that's been widening for a generation.
And now, all of that slow-motion industrial decay has finally converged on one single domain, the nuclear supply chain. And this is an area where the consequences are no longer theoretical, and where that decay has become a national security trap with a very hard, non-negotiable deadline.
So, let's peel back the layers of this problem, shall we? Because the part that people are just now starting to discuss, that's really just the thin, visible surface of a much, much deeper structural failure.
The market's starting to talk about the enrichment gap. Okay, fine. This is the first layer, the most obvious one. And yes, it's a real problem, but to focus on it is to miss the entire point. It's the symptom, not the disease.
If you dig just a little deeper, you find the conversion bottleneck. A single facility, a single point of failure with absolutely no redundancy. Now, this is critical, yes, and it's where most of the serious analysis of this problem currently stops. But it's only the second layer. The real crisis lies far, far beneath this.
All right, now we get to the physics. The actual physical, mechanical constraints. The heavy industry and the materials science that they don't exist anymore in the United States. These are the tools we literally forgot how to make.
See, you cannot build a modern nuclear reactor without a reactor pressure vessel. And you can't build a modern pressure vessel without forging it. To do that, you need a forging press of this scale, 14,000 tons, something capable of handling a single steel ingot that weighs 600 tons.
And this is the number of those forging presses that currently exist in the United States. 0. The capability is gone. It does not exist on American soil.
Globally, there are only 3 such facilities. They're in Japan, China, and Russia. This is not a supply chain issue. This is a condition of total dependency. Our ability to build the very backbone of our energy and defense infrastructure, it rests completely in the hands of other countries.
And the hardware gap, it goes even deeper than just heavy forging. To enrich uranium, you need gas centrifuges spinning at incredible speeds. The performance of these machines comes down to the materials you use for their rotors. Marriaging steel gets you to maybe 500 meters per second. Advanced carbon fiber, that can get you over 700. This isn't a procurement problem you can solve by writing a check. This is a materials physics problem that takes years of qualification and highly specialized manufacturing.
And then, underneath all of that, there's another hidden dependency: zirconium. It's the material for the cladding that surrounds the fuel assemblies. Without it, you can't run a reactor. Simple as that. And a huge portion of that supply chain runs right through Russia. It's the dependency one layer below the one everyone is watching.
But even if we could magically snap our fingers and recreate all the hardware, we'd still face an even more intractable problem: the collapse of the human infrastructure. This is the resource that is even harder and takes even longer to rebuild.
The most critical asset we're losing is something called tacit knowledge. It's the institutional memory. It's the experience-based gut feeling that you can't write down in a procedure manual. It's the difference between knowing the theory of how a plant is supposed to run and knowing how this specific plant actually runs, with all its quirks. And that knowledge is walking out the door every single day.
The numbers here, they paint a pretty stark picture. The U.S. nuclear workforce is way older than the rest of the energy sector.
Sure, 60% are between 30 and 54, but there are 23% fewer workers under 30. We basically created a generation-sized hole in hiring from the 80s to the 2000s, and now, well, the demographic cliff has arrived.
And this is the crucial distinction that so many people miss. A graduate with a nuclear engineering degree, they have theoretical knowledge. They are capable of learning the job, but an experienced operator, a commissioning engineer, they already know the job. And that gap, the one between a degree and deep operational knowledge, that can only be bridged by years of mentorship and hands-on experience. That chain of knowledge transfer is broken.
So into this collapsing system of hardware and human capital, we're now injecting a brand new problem, a massive, completely uncoordinated, and simultaneous surge in demand from multiple powerful sectors, all fighting for the same severely constrained resources.
Just think about what's happening all at once. You have all this talk of a nuclear renaissance with fleets of new small modular reactors. You have this surging, almost desperate electricity demand from AI data centers. At the same time, you have programs to extend the lives of the old reactors. And on top of that, proposals for new, large-scale construction. These efforts aren't coordinated. They're just colliding in the marketplace.
Which, of course, raises the critical question. With all these competing priorities, who decides? Who allocates the one forging slot that might become available in Japan? Who gets the handful of experienced commissioning engineers we have left? The answer is no one. There is no allocation mechanism. It's a free-for-all, with everyone competing for an infrastructure that can't even meet a fraction of the demand.
So when you finally stand back and you look at the entire picture, you realize this isn't some new crisis that just popped up out of nowhere. It's the inevitable, mathematical result of a decades-long, self-inflicted decay, an unforced error of genuinely historic proportions.
This timeline really tells the whole story. Construction on the last new American nuclear power plant began in 1979. In the decades that followed, the vast industrial base that was required to build and sustain a fleet like that was just allowed to atrophy. It didn't just shrink. For all practical purposes, it vanished.
And this brings us right back to the central thesis. The decay curve is already written. It's governed by the unyielding mathematics of time, of metallurgy, of knowledge transfer. No amount of 11th-hour funding can change the physics of the problem. The math is not on our side, and it's not improving. And that leads to the final, stark, strategic implication of all this. In this particular arena, our adversaries don't need to act against us. They don't need to interfere at all. They only need to wait. The system's own internal decay is doing all the work for them.